Now we'll be talking about the Dalton's law of partial pressures. So, a very important point for the Dalton's law is that it is defined for non-reactive gases. Till now, we were talking about singular gases, but now we'll be talking about a mixture of gases. So, the Dalton's law states that in a mixture of non-reactive gases, the total pressure of the gaseous mixture is the sum of partial pressures of the gases. Now, this term partial pressure is something which is new for you. So, let's first see what partial pressure means. Partial pressure is actually the pressure exerted by the same mass of the gas as is in the mixture, okay, when it is taken alone. Okay, so let's say that we have a mixture of neon and oxygen. We have to take care that these should not react with each other, and these do not because neon is a noble gas. Let's say we have a mixture and the mass of neon is m1 and the mass of oxygen is m2. So what the law states is that had you taken both of these gases individually, that is, we had one container and here's another container, one of these has neon and the other one has oxygen, the same mass. Had you taken both of these separately, and let's say that in these separate conditions we have the pressure of neon to be 1, this, and the pressure of oxygen to be 0.6 atm. Okay, so when you mix both of these in a container of the same volume, that is, now the container has neon plus oxygen both and same masses, that is m1 of neon and m2 of oxygen, the pressure exerted would be a sum of their partial pressures. That is, it would be 0.2 plus 0.6. The total pressure would be 0.8 atm. So this is what the law states, and this is the meaning of partial pressure. That is, we have to take the same mass and the same conditions, and then the pressure exerted by only that particular gas is the partial pressure of that gas. So, using these relations, we can derive a number of mathematical concepts. Let's see what they all are. The first one is that the pressure exerted by A, the gas A, now let's just call these A and B and not neon and oxygen to generalize. So, the pressure by gas A can be written as Na, that is the number of moles of A, times R times T divided by V, right? Using the ideal gas equation, that is PV is equal to nRT. You can write the pressure exerted by A as this. Similarly, the pressure exerted by B can be written as number of moles of B times R times T divided by V. Now remember that we've kept both of them at the same conditions of temperature and volume, right? So these will be same for both. And let's take another gas C, and the pressure for C will be number of moles of C into R into T divided by V. That is, we have a trinary mixture here. Now, when we mix all three of these, according to the law, the total pressure should be the sum of these three pressures, right? And we have to keep the temperature and volume as the same as was for the individual gases. Therefore, we can write it as Na times RT divided by V plus NB times RT divided by V plus NC times RT divided by V. And therefore, it can be written as Na plus NB plus NC times RT divided by V. That is the total number of moles times RT divided by V. And if you carefully see, if we had to write the total pressure, we would have written it this way only, because the number of moles into RT divided by V. So, if we now try to find out a relation between the partial pressure of A and the total pressure, which we've just found out, we can write it as Na times RT divided by V divided by N total times RT, and there goes a V here. So if we cancel out terms, this RT gets cancelled out and this V also gets cancelled out, and what we are left with is NA divided by N total, that is Na plus Nb plus Nc. And if you try to remind your mole concepts, this quantity was said to be the mole fraction of A. So we can say that the partial pressure of A is equal to its mole fraction times the total pressure, and similar expressions can be derived for B and C and any number of components which you have in the mixture. So this is a major takeaway from here and the Dalton's law of partial pressures.